Dear students, good morning. Today we will discuss the topic white noise and signal to noise ratio. Prior to that, we have a recap on various types of noises. So, noise is nothing but it is an unwanted signal that gets added to your actual signal and disturb the transmission. There are two types of noise, one is external and another one is internal noise. External noise means the source will be external. It is again classified into three types: atmospheric noise, extraterrestrial, and man made noises. Again, now this extraterrestrial noise is divided into solar and cosmic noise. Solar noise is due to the electrical noise from the sun, and cosmic noise is due to the various noises received from our galaxy and different galaxies. And next main classification is internal noise. Here, there will be a spontaneous fluctuations in voltage and current in the electrical circuit. This gives rise to a noise that we claim as internal noise. There are two types. Actually, there are various types. The most predominant internal noise are short noise and then thermal noise. If the noise arises due to the discrete nature of current flow, then it is called as short noise. If the noise is attributed because of the random motion of electrons in a conductor, then it is thermal noise. So this gives the mean square short noise current, that is In square equal to 2 times of IDC plus 2 I naught into QB, where In is the direct current is the PN junction and IDC is the reverse saturation current, Q is electronic charge and B is the effective noise bandwidth. Short noise is found to have a uniform spectral density. Next comes the thermal noise. So this is generated by means of all the resistors. So the experimental results by Johnson has given the mean square noise voltage as V square equal to 4kTBR, where K is the Boltzmann constant, T is absolute temperature, B is bandwidth and R is resistance. Now we can relate the noise power with that of the temperature and bandwidth, that is N is equal to K into TB. So this thermal noise is often referred to as white noise because the power spectral density is uniform. So for all the frequencies, your power spectral density will be same. It remains constant. That is why the thermal noise is called as white noise. And next comes the low frequency of flicker noise. Most of the ICs, diodes, transistors, these exhibits a low frequency noise which is frequency dependent. So those frequencies are called as flicker noise or 1 over F noise. Next comes the another noise called as excess resistor noise. So which means that apart from the thermal noise, your resistor will have an additional noise. So this additional noise is also frequency dependent. This is referred to as excess noise. And next comes the burst noise or popcorn noise. So here the semiconductor will produce a burst sound or a popcorn sound with that will have a pass spectral density proportional to 1 by f square. So these are the various types of sources that we have already types of noises that we have already discussed. And now in today's class we will have a detailed explanation on white noise. So white noise, now we have already discussed, that is our pass spectral density will be constant. So from the graph you can check for all the frequencies your pass spectral density will have the same value. It is independent of frequency. That is very important. So it doesn't depend on the frequency. So now you can have a doubt why it is called as white. So as you know in physics, we know that white light is nothing but combination of all the colors. If you apply it to the spectrum, you will have all these 7 colors, right? In similar way, this white noise has the uniform pass spectral density, right? Because of that reason, it is claimed as a white noise. So this white noise is nothing but it is denoted by W of t. It is a stationary process. So this we can write the pass spectral density SW of f of this white noise as it is a constant value n naught by 2. At which condition? For all the frequencies. That is, if your frequency lies between minus infinity to plus infinity, for all the cases, your pass spectral density is constant. It is denoted by n naught divided by 2. So that is what represented here. So your pass spectral density is equal to n naught by 2 for all values of f. Now we need to find the autocorrelation function for this. So we already discussed on the random process. We have studied the Wiener-Kirchner relations. It is nothing but autocorrelation. If you require autocorrelation function, take inverse Fourier transform for the power spectral density. That is the concept, right? So you know the power spectral density, that is n naught by 2. So take inverse Fourier transform for that. You will have n naught by 2 into del of tau. This is nothing but the autocorrelation function. So this is represented here, or ww of tau is equal to n naught by 2 into del of tau. So this is nothing but autocorrelation function of the white noise. It consists of the delta function del of tau, which is multiplied with the factor n naught by 2 at tau equal to 0. So now we can represent this graphically. So this represents the characteristics of the white noise, that is power spectral density. It is constant for all the frequencies, and here we have calculated the autocorrelation function. So this is a delta function multiplied by a factor of n naught by 2. So how we will represent our delta function? At 0 you will have a value del of tau, and remaining you don't have any value. The same here, at 0 you have the value that is del of tau, which is multiplied by a factor n naught by 2. So this represents the autocorrelation function. So this white noise is also Gaussian. It is also Gaussian. It means that wherever you can take the two samples, the samples will be uncorrelated with each other. They are statistically independent. So as long as the bandwidth of a noise process at the input of your system is appreciably larger than the bandwidth of the system itself, in that case we can model the noise process as white noise. Thank you.